Most people are familiar with permanent magnets because they have many uses at home, in the office, and in the workplace. Use of permanent magnets range from simple use, attaching a magnetic bottle opener to a refrigerator door, to complex uses, such as being used in a generator to transform mechanical energy into electrical energy or vice versa. Permanent magnets do not have a power switch. They cannot be turned on or turned off. Permanent magnets retain their magnetic properties until the residual magnetism is removed from the material. One way of removing the residual magnetism from a permanent magnet is by the application of an external magnetizing force, called coercive force, which will be covered later in this module. Another type of magnet is the electromagnet. Electromagnets are made of coils of wire wrapped around a ferromagnetic core. Electromagnets can be activated/deactivated by switching the coil current on or off. The first electromagnet was invented by English physicist William Sturgeon in 1825. Sturgeon wound several turns of insulated wire around a horseshoe-shaped iron core and noticed when electric current ran through the wire, a magnetic field was induced in the iron core, creating a temporary magnet. In 1829, American scientist Joseph Henry made significant improvements to the electromagnet by insulating the wire with silk. Henry also observed that electromagnets made with long coils would produce a stronger magnetic field than short coils. In 1831, Henry discovered electromagnetic induction, independently of Michael Faraday. This illustration shows a simple electromagnet consisting of a battery, a switch, and an inductor or coil. Notice that the coil has not yet generated a magnetic field because the switch is still open or off. Now watch what happens when the switch is closed and current flows through the coil. You guessed it. When the switch is closed, current flows through the coil and a magnetic field is generated through and around the coil. In this setup, the only way to induce eddy currents in a nearby conductor would be to constantly open and close the switch, which would provide the alternating polarity current needed for electromagnetic induction to occur. While we are here, take note of the magnetic field characteristics, because in a moment we are going to insert a ferromagnetic core material inside of the coil. When we close the switch, in the next slide, the presence of the ferromagnetic core material will concentrate the magnetic field, increasing the strength of the magnet many-fold. When electrons are flowing through a conductor, the electrical current flow has an associated magnetic force called magnetism. Magnetism is the invisible force that has the ability to do mechanical work in the form of attraction or repulsion. Materials having magnetic properties, and are thus able to be magnetized, are referred to as ferromagnetic materials. These materials usually have some level of iron, nickel, or cobalt in them. Materials that do not have magnetic properties are referred to as non-ferromagnetic materials. The regions outside the ends of a magnet that exhibit the force of attraction or repulsion are referred to as magnetic poles, designated as either north, N, or south, S poles. Each microscopic magnetic domain has a north and south pole, which together form a complete magnetic system. The individual magnetic domains are the smallest known permanent magnets. 6,000 domains would occupy an area comparable in size to the head of a common pin. Each domain is composed of about 1 quadrillion individual atoms. That's 1 times 10 raised to the 15th power. If the atom were the size of a half-inch ball, then the domain would contain enough of those balls to surround the Earth with a band 30 miles wide. A magnetic dipole moment is a measure of strength and orientation of a magnetic system, each domain, including its north and south poles. The strength of a magnetic dipole moment is the product of the strength of either pole and the distance between them. In order to magnetize a non-magnetized ferromagnetic material, the magnetic domains must be lined up by application of an external magnetizing force. This external magnetizing force can be produced from a permanent magnet or an electromagnet, which is a magnetization coil. In a magnetized ferromagnetic material, the individual magnetic domains are magnetically aligned, with north poles attracted to south poles. The most basic law of magnetism is that unlike magnetic poles, such as north to south or south to north, will attract each other, while like poles such as north to north or south to south will repel each other through the mechanical force caused by magnetization. This law can easily be demonstrated by taking 2 bar magnets and bringing their ends near each other. The magnets will either attract or repel one another based on how their magnetic poles are oriented. Magnetic lines of force are invisible, but indicate the orientation and concentration of the magnetic field, the region around the magnet that can attract or repel other ferromagnetic objects. Evidence of the magnetic lines of force can be confirmed by placing a sheet of paper over a magnetized material and sprinkling fine iron particles on the sheet of paper. The iron particles will line up, indicating the presence of the lines of force. Lines of force tend to be concentrated at the ends of the magnetized material, where the magnetic lines of force enter or leave the material. This illustration shows that you can identify where the magnetic lines of force are by sprinkling fine iron particles over the magnet. The iron particles line up with magnetic flux lines. Magnetic field orientation will vary depending on the configuration of the magnetic material and how the material was directionally magnetized. The magnetic flux in a ferromagnetic material is the entire group of the magnetic lines of force which pass through a given area of the material. The Greek letter phi is the symbol for magnetic flux. The SI unit of magnetic flux is the Weber. The SI abbreviation comes from the original French system International des Unités. Magnetic flux density is the term used to quantify the level of magnetic flux in a ferromagnetic material. The magnetic flux density is the number of lines of force passing through a unit area of material. The symbol for magnetic flux density is the letter B. The SI unit of magnetic flux density is the Tesla, or T. The Maxwell, mx, is one magnetic field line or line of force. The Weber, Wb, is 1 times 10 to the 8 lines or Maxwells. The Gauss, or G, is 1 line of force per square centimeter. The Tesla, T, is 1 Weber per square meter, and 1 Tesla is equal to 10,000 Gauss. Magnetic flux, or phi, is the entire set of a magnet's lines of force. Magnets are usually measured in terms of Gauss. To put things in perspective, the Earth's magnetic field is quite weak, only measuring between about 0.25 to 0.65 Gauss. whereas a small refrigerator magnet may be around 100 Gauss. Magnets in magnetic resonance imaging or MRI machines are in the 0.5 to 3.0 Tesla range, which equates to 5,000 to 30,000 Gauss. Extremely powerful magnets up to around 60 Tesla are used in research. The right-hand rule is used to determine the direction of magnetic field flow around a conductive wire or rod when the direction of current flow is known. The magnetic field flow direction around the conductor is dependent on the direction of current flow. The figure below shows the application of the right-hand rule. Fortunately for the person in the illustration, they still have all of their fingers. Another view of magnetic field flow based on application of the right-hand rule is shown below. Magnetic permeability is defined as the willingness of a material to conduct magnetic flux lines. A similar definition for magnetic permeability is the ease at which materials can be magnetized. Permeability is quantified by the ratio of the material's flux density, or B, to the test coil's magnetizing force, or H. If the value of B is higher than H, permeability would be greater than 1. The Greek letter mu is the symbol used to designate permeability. Most materials inspected with eddy current testing have a permeability value very close to 1, which means that permeability will have a negligible effect on the eddy current test. From a magnetic standpoint, materials are categorized as one of the following 3 types of materials: diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic materials have a magnetic permeability slightly less than 1, which is less than the permeability of vacuum. Diamagnetic materials typically have relative permeability values between approximately 0.99997 and 1.0. Organic compounds such as water, wood, paper, and most plastics are diamagnetic. Gold, silver, and copper are examples of diamagnetic materials. Diamagnetic materials are slightly repelled from an external magnetizing field and do not retain any magnetic properties once the external magnetic field is removed. Paramagnetic materials have a magnetic permeability slightly more than 1 and have relative permeability values between 1.0 and approximately 1.00016. Aluminium and platinum are examples of paramagnetic materials. Paramagnetic materials are slightly attracted to an external magnetizing field, but do not retain any magnetic properties once the external magnetic field is removed. For the purposes of eddy current testing, paramagnetic and diamagnetic materials can be considered non-magnetic. When the permeability of a material is equal to unity, or 1, it will not be a variable affecting the coil's inductance, which is the ability of a coil to produce a voltage in itself or a neighboring circuit. Practically speaking, if the permeability of a material is equal to unity or 1, it will not be a factor needed to be considered when performing eddy current calculations, such as standard depth of penetration, etc. Ferromagnetic materials have a magnetic permeability much greater than 1, are strongly attracted to an external magnetic field, and retain magnetic properties once the external magnetic field has been removed. Ferromagnetic materials have relative permeability values ranging from approximately 50 to more than 100,000. Iron, nickel, cobalt, gadolinium, and most of their alloys are ferromagnetic. Reluctance is the measure of a material's opposition to propagating magnetic flux lines. Reluctance can be thought of as the opposite of permeability. Like eddy currents, magnetic flux lines travel in closed loops and always move through the path of least resistance. Air and water have high reluctance, while soft iron has a very low reluctance. Magnetizing force is defined as the force that sets up a magnetic flux in a magnetic circuit or test part, and is designated by the letter H. Magnetizing force is measured in units of oersteds and is used to magnetize or demagnetize a ferromagnetic material. The terms residual magnetism, remnant magnetization, and remanence all refer to the magnetization left behind in a ferromagnetic material after an external magnetizing force is removed. Permanent magnets are therefore said to have residual magnetism, remnant magnetization, or remanence. Permanent magnets work because they have residual magnetism and are therefore attracted to other ferromagnetic materials. If a material is magnetized for the purposes of nondestructive testing, there may be cases when the residual magnetism needs to be removed from the test object before it is placed into initial service or returned to service. Some examples of when demagnetization would be required are when the residual magnetism may affect the operation or accuracy of instruments when the specimen is placed into service, interfere with the proper functioning of a part, or cause particles to be attracted and held to the surface of moving part. Retentivity is defined as the ability of a ferromagnetic material to retain a magnetic flux after the external magnetizing force has been removed. Stated another way, if a ferromagnetic material retains a magnetic flux after the external magnetizing force has been removed, it is said to have retentivity. Materials used for permanent magnets such as nickel, cobalt, steel or iron are said to have magnetic retentivity. Non-magnetic materials such as aluminium or copper have no retentivity. Remanence, retentivity, and residual magnetism are all related terms. Coercive force is the amount of magnetizing force needed to remove the residual magnetism from a ferromagnetic material. Coercive force is designated by the letter H and is measured in units of oersteds, whereas magnetizing force magnetizes a ferromagnetic material. Coercive force demagnetizes a ferromagnetic material. The coercive force required to remove the residual magnetism from a low permeability material is greater than the coercive force required to remove residual magnetism from material having higher permeability. In other words, a weak magnet made of mild steel having a high permeability value would only take a small amount of coercive force to remove the residual magnetism from the material. In contrast, a strong magnet made of high carbon steel having a low permeability value would take a much greater amount of coercive force to remove the residual magnetism from the material. Demagnetization can be intentionally accomplished in the following ways. Number 1. Heating the magnetized material past the Curie point. Number 2. Placing the magnetized material in a solenoid or coil and applying a strong magnetic field by applying strong alternating current and slowly reducing the current. A third way to demagnetize a material is by pounding the material with a hammer. Heating the magnetized material past the Curie point disrupts the interfaces between the individual magnetic domains, the domain walls, and makes it easy for the magnetic domains which are ordinarily lined up to rotate and become misaligned. If several magnets are stored together or randomly rub against each other, Each can affect the other, changing the orientation of the magnetic domains and reducing the net magnetic field strength. A strong magnet can be used to demagnetize a weaker magnet that requires less coercive force to demagnetize. Tools can be purchased specifically for magnetizing and demagnetizing ferromagnetic material. Self-demagnetization can occur over time, stronger magnets taking longer. Materials that have magnetic properties are those materials that have some value of permeability. Materials exhibiting permeability properties can be magnetized by an external magnetizing force, can retain some level of magnetic flux, and can be demagnetized by an external magnetizing force. Magnetic hysteresis is the phenomenon where a flux density lags behind the magnetizing force during magnetization of a ferromagnetic material. When a ferromagnetic material is magnetized by applying an external magnetizing force, a certain amount of flux density will remain in the material after the magnetizing force is reduced to zero. A hysteresis loop is a graphical representation developed to show the relationship between the magnetizing force and the magnetic flux density of a ferromagnetic material. The curvature of the hysteresis loop is characteristic of the type of material being observed and can vary in size and shape, i.e. narrow or wide. If the flux density in the material returned to zero at the same time the magnetizing force returned to zero, there would be no hysteresis loop, and no remaining magnetic flux in the material. Hysteresis loops provide information on the magnetizing force required to fully magnetize a material, the magnetic saturation point of the material, and the residual magnetism remaining in a material after it has been magnetized. The hysteresis loop plots the external magnetizing force on the horizontal axis, H, and magnetic field strength on the vertical axis, B. Hysteresis loops are typically shown as the material is in a state of magnetic saturation, but the material must be fully magnetized, magnetically saturated, before the hysteresis loop takes on this final shape. Do not think of a hysteresis loop as being a static image. The loop evolves from a point of no magnetization to full magnetic saturation as the magnetizing current, H, is applied. Here you can see that when a small amount of magnetizing force is initially applied, the magnetic flux, B, starts to slightly increase. Magnetizing force is increased cycle after cycle of magnetizing current, until magnetic saturation in the material is finally achieved from a certain final amount of magnetizing force. Hysteresis loops are normally presented as smooth curves, but hysteresis loops are made up of small discrete jumps in magnetism, not smooth. The jumps are the alignment or flipping of each individual domain as the material is being magnetized. Changes in magnetic properties, such as the alignment of domains under an external magnetizing force, generate Barkhausen noise, which can be monitored with specific equipment. The unmagnetized material below shows the magnetic domains randomly distributed in the material. This slide shows the initial application of a magnetizing force to an unmagnetized piece of ferromagnetic material. The red curve shown on the hysteresis loop plot shows the initial magnetization curve, also referred to as the virgin curve. The initial application of the magnetizing force is what starts to align the internal magnetic domains, thus the beginning of the magnetization of the material. Here, since there is not yet any magnetizing force, there is no domain alignment. But when the initial magnetizing force is applied, domains start to align. The heating effect will always occur when alternating current is used for magnetization, since the changing direction of the alternating current, and thus the changing direction of the magnetizing force, is constantly forcing the magnetic domains to reverse direction twice per cycle of alternating current. In the top image, the material's magnetic domains are in an unmagnetized state. In the bottom image, the material is fully magnetically saturated once the saturation point is reached. In the top image, the magnetic saturation point has been reached. Increasing magnetizing force beyond this point will not increase magnetic flux in material. The saturation point corresponds to 1/4 of one cycle of magnetizing current, or 90 degrees. If the alternating magnetizing current was turned off exactly at the moment of magnetic saturation, the magnetic domains would be lined up, and heat loss from the work required to rotate the individual magnetic domains would stop. The point of retentivity is the point at which the magnetizing force is returned to zero, and some amount of residual magnetism remains in the material. At this point, a magnet has been created. The term hysteresis, which means to lag behind, is demonstrated well in the image to the right. When the magnetizing force, or H, is reduced to zero at the retentivity point, some magnetism lags behind or remains in the material. The point of retentivity where the magnetizing force is reduced to zero corresponds to 1/2 of one cycle of magnetizing current, or 180 degrees. Coercive force is the amount of magnetizing force needed to remove the residual magnetism from a ferromagnetic material. Coercive force is designated by the letter H and is measured in units of oersteds. Whereas magnetizing force magnetizes a ferromagnetic material, coercive force demagnetizes a ferromagnetic material. Here, the magnetic saturation point is reached in opposite direction, or the second half of the cycle of magnetizing current. The negative saturation point corresponds to 3/4 of one cycle of magnetizing current, or 270 degrees. Here we see the point of retentivity caused by the second half of the magnetizing cycle. The negative retentivity point corresponds to the completion of one complete cycle of magnetizing current, or 360 degrees. The hysteresis loop has now completed one complete cycle of magnetization/demagnetization, and will continue to retrace itself as long as the external alternating magnetizing current is flowing. This is a very important slide, as you will be expected to recognize and label all of the points on a hysteresis curve. Which material has the lowest permeability based on the hysteresis loop? The hard ferromagnetic material. Which type of ferromagnetic material would be more desirable for a permanent magnet? The soft ferromagnetic material. The desired function of an electromagnet is for it to exhibit magnetic attraction only when current is flowing in the electromagnet. The soft ferromagnetic core will retain very little residual magnetism when the electromagnet is de-energized. All magnetic materials have hysteresis loops. Soft magnetic materials require less magnetic force to magnetize and less coercive force to demagnetize. whereas hard ferromagnetic materials require more magnetic force to magnetize and more coercive force to demagnetize. Which type of ferromagnetic material would be more desirable for a permanent magnet? The hard ferromagnetic material. The desired function of a permanent magnet is for it to exhibit magnetic attraction after the magnetizing force that created the residual magnetism is no longer present. The hard ferromagnetic core will retain much more residual magnetism than if a soft, higher permeability material was used. The slide shows the superimposed soft and hard ferromagnetic materials, so you can see the comparison graphically speaking. Soft ferromagnetic materials have higher permeability, lower retentivity, lower coercivity, lower reluctance, and lower residual magnetism. Hard ferromagnetic materials have lower permeability, higher retentivity, higher coercivity, higher reluctance, and higher residual magnetism